Well, welcome everybody. Glad you could make it to the talk. Today we have Fisher Pham. He was a Calc 1 student of mine last semester, and he didn't learn his lesson. Signed up for my class again this semester for statistics, so he could hear all my jokes again. But he's a great student, and he mentioned something about working on Rubik's Cube, and so here it is for the talk.
All right, thank you, Professor Berger, for the introduction. So, if you can't tell, I love solving Rubik's Cubes. I've been doing it for about a year and a half now. A big question I get all the time is, how do you solve it? So, I solve Rubik's Cubes using the Friedrich method. This was developed by Jessica Friedrich and David Singmaster in the 1980s. So, the Friedrich method consists of 4 steps. It's also called the CFOP method. So there are 4 letters corresponding to the 4 steps. So the first step is to make a cross. So I usually start with the white cross, but you can do it on any side. Doesn't really matter. I just do it on the white side for consistency. And it's pretty simple. You just make a cross. That's all there is to it. The next step is the first 2 layers, or F2L. And that is when you solve the first 2 layers of the Rubik's Cube, just intuitively. Now the next 2 steps, I solve the last layer of the cube using algorithms or patterns that I memorize. So the next step is orientation of the last layer. So in this step, I get all of the stickers on the last layer. So if I started with white, in this case it would be yellow. I get all the yellow stickers together on top of the last layer. And I use algorithms to, so there are 58 different cases that you can get, one of which is when the orientation of the last layer is already done. So there are 57 different algorithms that you can memorize to solve the last layer of orientation of the last layer. You only need like 1 or 2, but the more you memorize, the faster you can go. And the last step is permutation of the last layer, and that is switching those pieces around in the last layer without reorienting them, and that finishes solving the cube. So in this case, in this step, there are 22 different cases. So there are 21 different, because one of the cases is already the cube already being solved. There are 21 different algorithms that you can memorize to permute the last layer. And again, you only need 2, but the more you memorize, the faster you can go. So I have a scrambled up Rubik's Cube here, and I'll just go through a solve just to kind of show you how it works. So right now I've just made the cross. I'm moving on to the first 2 layers, which is the longest step. So I've just finished the first 2 layers, so I'm moving on to orientation of the last layer. And now permutation. So that's how I solve a Rubik's Cube using the Friedrich method. But this is a lot of work. It's a lot of memorization. And the natural question is there one algorithm, one pattern that I can repeat over and over and over and over and solve any scramble of a Rubik's Cube? So this hypothetical algorithm is called Gans algorithm. So we're going to be talking about this today. I do want to make a distinction, though. Gans algorithm is often confused with something called Gans number. Gans number is the maximum number of turns for the optimal solution for any starting position of a Rubik's Cube. This number is 20. So in other words, any Rubik's Cube can be solved in 20 moves or fewer. This is not relevant to our discussion, but I just wanted to make that distinction. It's often confused with Gans algorithm. And this was found to be 20 by this group of people using computer power from Google. So it's just an interesting fact that's not really related or important to our discussion, but it's something I thought I'd throw in there just to make that distinction. So back to Gans algorithm. This is what we're going to be talking about. But before we can ask if this algorithm exists or if we can find it, we need to talk about a few things first. First, which types of pieces does a Rubik's Cube have? What is a permutation? How many permutations does a Rubik's Cube have? And what is an algorithm? So first, what kinds of pieces does a Rubik's Cube have? Rubik's Cube have 3 types of pieces. So first off, you have the centers. They're all connected to each other through this core. This is just a taken apart Rubik's Cube. So there are 6 different centers, 1 on each face. And they can rotate, but they can't like move around. They can't switch places. And their rotation doesn't really matter that much. If a piece is rotated one way, it's still a solved cube as long as all the other pieces are where they need to be. So centers don't really matter, but it's just important. I didn't want to leave them out. Next, we have the edges. So these edge pieces, they're right here. They connect the centers. They each have 2 different colors, so they can be rotated 2 different ways, and there are 12 of them. Next, we have the corner pieces. So corner pieces are on the corners. There are 8 of them, and they each have 3 different colors, so they can be rotated 3 different ways. That's all there is to the pieces. I just wanted to make sure we understood how they're put together and what it consists of. So now we can talk about what is a permutation. So a permutation is any scramble of a Rubik's Cube. So to start off, there's the solved permutation. So that's when all the pieces and colors are together. And every time you turn it, you're creating a new permutation. So this is a different permutation. This is a different permutation. This is a different permutation. So every time you do a move, it will create a new permutation. So obviously, there are a lot of permutations. We are going to be talking about, we're only going to be considering possible permutations. So there are 2 types of permutations, possible permutations and impossible permutations. So possible permutations are any permutation that you can get just by rotating the cube just on the 6 faces. So any moves like that, if you can get to a different permutation, then that one is a possible permutation. However, there are some illegal moves. So by illegal, I mean they're not allowed in competitions, and they will sometimes create permutations that cannot be solved just by moving the cube in the regular 6 faces. So some of these illegal moves are, for example, like twisting a corner like that. That cannot be solved by just moving the 6 faces around. You have to actually untwist the corner. Another illegal move is taking out an edge piece and flipping it around and then putting it back in, or swapping edge pieces. That will also create impossible permutations. So you can't get back to the solved state without doing those illegal moves again. However, sometimes if you're doing one of these illegal moves, so if you twist a corner, sometimes it won't create an impossible permutation. So if you rotate a corner a multiple of 3 times, any corner a multiple of 3 times, then it will be a possible permutation. If you flip an even number of edges, then it will be a possible permutation. And if you do an even number of swaps on edges, it will be a possible permutation. So for example, if I twist this corner once counterclockwise, and then I twist this corner twice counterclockwise, that's 3 twists counterclockwise, that actually creates a case that I can solve just by turning the 6 faces of the cube normally. So sometimes they don't create an impossible permutation if you do those illegal moves. I just want to make sure that we know that not every single illegal move will create an impossible permutation. So now we can talk about how many permutations does a Rubik's Cube have. So I have some numbers up here. I know that it's a lot of numbers. I know that it was on the flyer, but if you have the flyer with you, don't cheat, don't look at it. What do you think the number of permutations one of these is the number of permutations in a 3x3x3 Rubik's Cube. So does anyone, I know a lot of you know what it is, but yeah, do you have a guess? Number one? Okay. All right. Anyone else want to give it a shot? Yeah. Yeah, it's C. So, but let's calculate this out. So let's say you've taken a Rubik's Cube apart, which I have. First thing, let's just say, this isn't necessarily the best way to put it back together, but let's say you put in all the edges first. So there are 12 different edges. So when you pick up the first edge, it has 12 different spots that can go. And then the next one has 11 different spots that can go. The next one has 10. So that our first factor here is 12 factorial. And for those of you who don't know, this is when there's an exclamation point after integer. That means you multiply every lower integer. So 12, that would be 12 times 11 times 10, all the way down to 1. So that's our first factor. And now let's move on to corners. We'll do the same thing. So there are 8 corners. So the first one you pick up can go in 8 different spots. The second one can go in 7, etc. So that's 8 factorial. Now, the next thing we need to do is we need to cover which way the pieces can be oriented or rotated. So edges, there are 2 ways to flip an edge, so because there are 2 colors on it. So if you flip one edge, you have to multiply all this by 2, because now you've created 2 sets of whatever you had. And we have to do this 12 times. So that's 2 to the 12th power. Now we can do the same thing with corners, but corners can be rotated 3 different ways. So that's 3 to the 8th because there are 8 corners. And if we multiply all this out, we get 519 quintillion. And if we go back to our list of numbers here, that is not on there. So we've done something wrong. Does anyone know what went wrong here? Yeah? Exactly. Yeah, we've included impossible permutations in this. So like I was saying, there are certain cases that are impossible. So when you twist a corner like that, you've just created an entire new orbit of permutations that you can do, and those are all impossible permutations. So because not every illegal move will result in an impossible case, in total we've created 12 different orbits, or 12 orbits that shouldn't be there. So we need to divide all of this by 12. So when we do that, we get 43 quintillion, 252 quadrillion, 3 trillion, 274 billion, 489 million, 856,000, which is C. But I didn't just pull random numbers out of the air. All these numbers have significance. So B is the number of permutations in a 2x2 Rubik's Cube. C is for the 3x3. D is for the 4x4. E is for 5x5. F is for 6x6. And G is for the 7x7. And A is for the 1x1. Forgot about that one. So just to demonstrate how large these numbers are, if you took a 55 millimeter Rubik's Cube, for every permutation of a Rubik's Cube that there are, you could actually go around, if you lined them all up, you could go around the entire Earth about 60 billion times. And then if you took, let's go to the 7x7. The 7x7 has 1.9 times 10 to the 160th power, about. So if you took, let's say you took, okay, so in the observable universe, there are about 10 to the 80, to the 80th power of atoms. So if you took each of those atoms and you made it into another observable universe filled with atoms, so that'd be squaring that number, so 10 to the 80th squared, that would be 10 to the 160th, which is a little bit more than half of that number there. So yeah, these are big numbers. There's a lot of potential with something that can fit in the palm of your hand. So moving on, now we have to talk about what is an algorithm. So like I said, I use algorithms to solve orientation of the last layer and permutation of the last layer. So these are basically just patterns that I memorize. And obviously they have to be written down in some way so that I can memorize them. So they are written down with something called Singmaster notation. This was developed by David Singmaster. So Singmaster notation has 6 different letters, each corresponding to one of the faces. So U corresponds to the upper face, D corresponds to the down face, R corresponds to the right face, then left face, back face, front face. And when you see one of these letters just by itself, that means turn that face 90 degrees clockwise with respect to that face. So even though clockwise might seem different to you when you're holding it like this, you have to turn it 90 degrees clockwise with respect to that face. So this is if this is the front face, then this is 90 degrees clockwise for the upper face, and this is 90 degrees clockwise for the down face. So it takes a little bit of time to get used to, but yeah, it's pretty simple. So if you want to go counterclockwise, then all you do is you add an apostrophe on the ends of these letters. So that's U prime, D prime, R prime. That's how it's read. And that just means same thing, but counterclockwise. If you want to do 180 degrees, you just put a 2 on the end. So U2, D2, R2, L2. And that's how it's read. That's how I memorize these different algorithms. In each algorithm, when you repeat it a certain amount of times, it will always go back to the permutation that you started on at some point. If you just keep repeating it over and over, it will always go back to the permutation that you started from. So that number of repetitions is called the order of an algorithm. So an order of an algorithm is the number of repeats of that algorithm required to return the cube to the original permutation that you started on. For example, an algorithm with order 10 must be repeated 10 times before it returns to the starting permutation. And the largest order of any algorithm is 1,260. So there's a proof for this. In fact, it's really complicated. I'm not going to go into it, but there is a proof for this. Yeah, that's what an order is, and let's look at some examples here. So algorithms of varying orders. Let's just take a simple one-move algorithm. So our first algorithm here is just R. So the right face clockwise 90 degrees. So that's what the algorithm was. So this algorithm has an order of 4 in a length of 1. So it takes 4 turns total to return to the starting permutation. So if we're starting at the solve state here, you do the algorithm once, twice, 3 times, 4 times, and it's back to the original starting permutation. So let's get a little bit more complicated here. R, U, R prime, U prime. This is a really common algorithm. It has an order of 6 and a length of 4, so 24 turns total until it returns to the starting permutation. So R, U, R prime, U prime. And so that's once, twice, 3 times, 4 times, 5 times, 6 times, and it's back to the starting position. So the next one is one of those algorithms that has the largest order possible. So R, U2, D prime, B, D prime. So this has an order of 1,260, which is the largest possible. It has a length of 5, so that's 6,300 turns total until it returns to the starting permutation. I started doing this, and I lost count and interest after about 5 repetitions. Someone out there has done this, has repeated it 1,260 times until it went back to the starting permutation. Someone's done it. So, Okay, so now we can finally ask, does God's algorithm exist? So first, let's set a definition for it. So God's algorithm must be able to be repeated an integer amount of times to arrive at the solved permutation from any other permutation. So basically we're saying you can't cut short on this algorithm. So if you keep repeating it over and over and over and you see the solved permutation, but you're in the middle of the algorithm, you can't cut short and stop there. You have to repeat it an integer amount of times or a whole number amount of times. So it must be simple enough for anyone to use the algorithm to solve any Rubik's Cube, any 3x3 Rubik's Cube, and it must be relatively short. So let's see, can this exist? God's algorithm must show at least 43 quintillion different permutations. And since 1,260 is not as large as 43 quintillion, God's algorithm does not exist because the algorithm can end on only a maximum of 1,260 different permutations before returning to the original permutation. So because of our definition, right now, we're saying that we can't cut short. So it's only going to end on 1,260 different permutations. And that's not quite as large as 43 quintillion. So this definition cannot exist. But I'm not quite satisfied yet, so let's go back to the definition and change it up a little bit. So let's take out the integer part. So this can be repeated any amount of times to arrive at the solved permutation from any other permutation. And it still has to be simple and relatively short. So basically now we're saying you can cut short. If you're repeating it over and over and over and you see the solved state or the solved permutation, you can cut short. You can end it there. You don't have to finish out the algorithm. So now let's see if God's algorithm can exist. So any algorithm of length L and order X can show at most XL different permutations when repeated any amount of times. So let's take a look at an example here. RU, R prime, U prime. Let's go back to that one. So it has an order of 6 and a length of 4. So 20, because you're going to turn it 24 different times before you get to the original starting permutation, only 24 different permutations are shown when repeated more than X times, so more than 6 times in this case. So you got the starting permutation, and then you're showing another permutation, and another, and another. That's going to happen 24 times before you get back to the first one, and then you're just repeating it, and you're showing the same permutations. So if I didn't start on the solved state, then this would never show, if I started completely scrambled, then this would never show the solved permutation. And it's never going to get there because it's just repeating itself over and over and over, showing the same 24 permutations. So if we're going by the same thing that X is the order and L is the length, then XL must show, or must be equal to or greater than 43 quintillion, because that's how many different permutations this algorithm is going to show. So if X is as large as possible, 1,260, then 1260X must be equal to or greater than 43 quintillion, and just doing simple algebra, we can get to the length of the algorithm must be 43 quadrillion moves long, or turns long. So if you're seeing this in Singmaster notation, there are going to be 34 quadrillion letters lined up for you to read and memorize. And let's not forget the prime moves and the 2 moves. So it's gonna be memorizing a lot. And okay, so that one algorithm, the RU, R prime, U prime, so that has 24 turns total until it gets back to the starting permutation if I keep repeating it 6 times. I can do that in about 3 seconds. So that's 8 turns per second. So if I were doing this algorithm at 8 turns per second, it would take me about 136,000 years. And I might have to do it 1,260 times. So I don't think this really is a practical way to solve the Rubik's Cube. It's basically just randomly turning it at this point. And we don't even we can't find anything this big. Like, there's no way that we're going to find an algorithm that large, and that's the least amount of moves that it will be. So it could be something much longer. And also, it's important to note, if we're going by this definition, there are an infinite number of different algorithms that could be God's algorithm. They're just going to get incredibly long as you continue to show. This is just the shortest possible length of God's algorithm at this point. So let's allow for something in our definition called a conjugate. So a conjugate is a sequence of algorithms in the form A, B, A prime, in which A and B are two different algorithms, and A prime is algorithm A performed in reverse. So what does that mean? That means basically we're going to do one algorithm, then we're going to do a different algorithm, and then undo the first algorithm. And if we use that, if we allow that in our definition of God's algorithm, that's going to allow us to show a lot more permutations with a shorter algorithm. But this is two algorithms. This is two different algorithms that we're doing, and we want a single algorithm solution. So we will restrict God's algorithm, or we'll restrict the conjugate in this case to a single move. So in the form A, B, A prime, algorithm A will be restricted to a single move in Sing master notation. So, and we'll also allow for rotation of the cube in between repetitions. So basically we're saying you can do a setup move and then do God's algorithm, and then you can undo the setup move. This is a really useful tool when making your own algorithms to solve different puzzles. But it will allow us to use a really short algorithm and show a massive amount of permutations by using these setup moves. And it's still kind of a single algorithm solution because it's just one move and then you're undoing it afterwards. So it's a little bit of a stretch, but if we allow this in the definition, it actually allows for a lot shorter God's algorithms to exist. So, and it's actually used in blindfolded solving. So let's look at an algorithm called the inverse Y Perm. The inverse Y Perm, that's the notation there. This swaps the two opposite corners of a 2 by 2 by 2 Rubik's Cube and is used in blindfolded solving. So let me just do the algorithm here if I don't mess it up. Okay. So it swaps this corner and this corner. So for blindfolded solving, I've never successfully blindfolded solved a 2 by 2, but to my understanding, they'll do this one algorithm over and over, and they'll do these setup moves to swap certain pieces around until it's solved. So this is a single algorithm solution as long as you allow for conjugates, so these setup moves. So allowing for conjugates and rotations allows for God's algorithm to be shorter and allows for an infinite amount of God's algorithms to exist. But it makes solving the cube using God's algorithm much more difficult. So basically, this makes it just incredibly so much harder than just solving it the regular way or using any other method pretty much. This is the hardest way to solve a Rubik's Cube because you're restricting yourself to one algorithm. And you're still having to think about which pieces move around and how the algorithm affects those pieces. I've tried solving a cube just using one algorithm and conjugates and rotations, and I haven't been able to do it. So I've been solving cubes for about a year and a half, and if I can't do it, this isn't a viable solution for someone who doesn't want to memorize more than one algorithm. So let's go back to the definition here. So do you think that this satisfies our definition if we allow for conjugates and rotations and cutting short the algorithm? Do you think it qualifies as a God's algorithm? Because to me, I don't think this satisfies the definition. It's It can be repeated any amount of times to arrive at the solved permutation from any other permutation, as long as you're allowing for conjugates and rotations, which is already a stretch. It can be relatively short. Any of these algorithms can. But it's definitely not simple enough for anyone to use the algorithm to solve any Rubik's Cube. So it doesn't satisfy the definition, in my opinion. But that's as close as we can get, pretty much. That's all there is. There's no simple solution. So in summary, since the maximum order of any algorithm is 1,260, there's no God's algorithm for the Rubik's Cube that can be repeated to end on the solved permutation from any other permutation. So that was our first definition, right? We wanted an integer amount of repeats to arrive at the solved permutation. So that definition can't exist. It just can't. Altering the definition allows for God's algorithm to exist, but the algorithm is far too long to be practical. So that was when we cut out the integer part. So we allowed for cutting short, and then we got the 34 quadrillion length algorithm that we're never going to find. So that doesn't really work as God's algorithm. And allowing for conjugates and rotations in between repeats of the algorithm allows for God's algorithm to be short, but solving the cube using one algorithm is much more difficult than learning how to solve it using other methods, or any other method. I don't think there's a harder way to solve a Rubik's Cube than using one algorithm. So basically, there's no effortless solution to the Rubik's Cube, except for the old-fashioned way of just painting over it. So, any questions? Yeah?
Just out of curiosity, I've seen you solve the cube quite a few times, but what's the fastest you can solve it?
I've solved it in about 13.38 seconds, I think. So, somewhere around there.
It's okay, I guess.
All right, anyone else? Yeah?
Can you explain where the number 1260 came from?
So that is the largest possible order of any algorithm. So any algorithm, if you repeat it over and over and over, it can't go any more than 1,260 without going back to the original permutation. So
I think he's asking for that proof that you didn't.
I'm not.
Construct that number easily or not?
I'm sorry?
Is there a way to construct that number easily or not?
Not easily. I mean, I've seen the proof, and I was like, yeah, I'm not qualified to go into this. This is too much for me. So I have a link to a PDF file that has the proof on it. I can give it to you after the questions here, if you like. Anyone else?
You mentioned making up your own algorithm. If you want to make up your own algorithm, which probably I'll go home tonight and give that a shot. So, have you done that yourself?
I don't want to call it making my own algorithm because it wasn't very complicated. It was just taking certain algorithms I already knew and applying them in different ways. So, kind of. I mean, I wouldn't call it making my own algorithms. I would call it like finding a method to solve. Like for this 3x3x5, I couldn't find many tutorials out there, and I was kind of stumped on how to solve like these lower three. So I kind of like made my own method. I wouldn't call it an algorithm, but that's as complex as I've gotten into solving puzzles.
Because I'm wondering, like, okay, so there's the Sing Master.
Mm-hmm.
How much time would someone spend actually creating something like that? Is this an afternoon's work or a couple of months? Or?
I guess it depends on how much experience you have. For me, it would take a long time because I'm not too great at solving different puzzles. But I've seen people just make up their own algorithms just on the spot, just figuring out different ways to solve different cubes. So yeah, it all depends on how well you can picture the pieces moving around in your head. So yeah, it could take weeks or months, but it might just take a few seconds.
In terms of
Yeah.
terms of algorithms to solve the cube, how many are on the web? That's a hard question to answer, but how many are out there that would be considered worthwhile or useful, or that are used frequently?
For the 3x3, there are, okay, so the most common method has, or the Friedrich method has 57 different OLL algorithms, or orientation algorithms, and 21 different permutation algorithms. So that's like probably the ones those are the only ones that I look at. But there are obviously there are other ways to get to solve orientation and permutation, but those are probably the shortest ways and the most efficient ways. Yeah?
Do you memorize all the algorithms?
For the 3x3, I've memorized somewhere between 20 and 30. So no, I haven't learned full orientation and permutation algorithms.
I'm curious about the illegal moves.
Mhm.
Like, so brand new Rubik's Cube out of the package, like, it's not designed to be doing those illegal moves, right? Does that come from, like, the mechanism being worn down so then people could flip them around?
Well, it all depends on the type of cube you have and how it's tensioned. So it's not necessarily designed to do those moves, but you can do them right out of the box. You can twist a corner. It might be a little rough, but you can do that just because the way that it's put together, obviously you can just manhandle the pieces until they twist.
But the cube itself wasn't like someone decided, oh, this is illegal. Like, the designers didn't intend for that to happen.
Yeah.
In the game, I see.
Yeah, and just in competitions, it just became a rule. You're not allowed to, yeah.
Can you take a 3x3 and talk us through solving it?
Yeah, I can do that.
Slow with it, so we can.
Yeah, yeah, definitely.
So 13 seconds is too.
Yeah, and I just want to clarify, 13 seconds is my best solve. So my average is somewhere around 22, somewhere around there.
Earlier was 20 seconds.
Okay, I was wondering about that. So first thing I do is I make the cross on the white side. So I know that when the white side is on top, red is across from orange and green is across from blue. That's how it always is. But when white is on top, green is to the left of red and blue is to the right of red. And orange, it's the other way for orange. So I'm looking for the edge pieces that have white on them. So I see that I can put the red across from the orange, and I can also put the green to the bottom layer, which is what makes it easier. And then I see that I can easily put these other two in their place by just turning it this way and doing those two moves. And now I am looking for pairs of corners and edges to put together. So I see that the white, blue, and orange corner is already paired up with the orange and blue corner. So I don't want to mess that up by fixing it across and aligning it with the centers, so I put that onto the top layer. I line the edges with the centers, and now I'm going to put that pair that I already made into its place, right there. The next pair I see, they're right next to each other, but they're not in the way that they should be oriented. So I'm going to break those two pieces apart and then put them back together in the right way. And a lot of it is just from experience. I can't tell you exactly, like, if I told you exactly what moves I'm doing, it probably wouldn't make sense at first unless you looked at it and saw how everything works. So I actually got the exact same case with another pair of edges and corners. So I'm just going to do the exact same moves I did. And now I need to break these two apart and put this corner on the other side. So I'm going to do that by doing these two moves here. Now for orientation, the cross is already made. Because I don't know all the orientation algorithms, so I'm actually, what I do is I make the yellow cross first, and then I orient the corners. So the cross is already made, which means it's a one-step process for me. So I see that these two stickers are facing here and these two are facing the opposite way on the other side. So I do a quick algorithm for that. And then I recognize the permutation case because there are two corners here that are permuted correctly and these two edges are permuted correctly. So I do the algorithm for that and it's solved. So that's a more in-depth run through of how I do it.
Which move is the one, you showed us a move, you said it was pretty often, I don't know, was it?
Are you R prime, E prime?
Yeah,
Yeah.
is that one of the ones that move the middle to the, on the sides, make the second letter?
Kind of. I've never really thought of it that way. No, I think you could use it in that way, but that's not the way that I put edges.
What do you use that move for?
It's used in a lot of different orientation and permutation algorithms.
On the
So
bottom, so it's part of one of the permutations.
yeah, it's part of a lot of them. So it's very commonly used. And also, a lot of people use it because it's pretty simple. So what they'll do is to like impress someone they like or something like that, they'll do, because the order is 6, so they'll do 3. They'll be like, oh, look at this scrambled Rubik's Cube, and then they'll do the other 3. So, yeah.
So in competition solves, are the best times basically a result of like luck of the draw, or are there other methods that are preferred to get faster times?
Like, the Friedrich method is the most common speed cubing method. It's the one that the world record solver uses. So that's the one that most people go with. And I wouldn't say any method is, well, any of the top speed cubing methods, none of them are necessarily faster than the other ones. It just all depends on how much you practice. But as far as luck goes, you can get lucky and you can get a really good solve, but you can't count on that in competitions. So my best solve was a 13-second solve. I got a last layer skip. So I went to the cross and first 2 layers, and then it was done. It was already solved. So I got extremely lucky on that one. But in competitions, that doesn't happen. That was I have like 2,500 recorded solves. So, and only 2 of them were last layer skips. And you do, I think, like either 5 or 12 solves in competition. So you can't count on that being just a lucky solve.
In the competition, does everybody start with the same original cubes? The same permutation on the cubes?
I don't know. I think so. Yeah, I think everyone's working on the same. Just to make it fair, I think everyone works on the same permutation. Yeah.
Did you say that the minimum number of moves for any permutation was 20? Is that the Google power calculation?
Yeah, that is the minimum or the maximum amount of moves for the optimal solution. So for every permutation, there is a optimal solution to get to the solved permutation as quick as possible, right? And the maximum number of turns it takes for that is 20. And that actually, the hardest, well, it's not really the hardest permutation, but the one that takes the most moves for the optimal solution, the 20 number, that's actually called the super flip position. That's when you take every single edge and you flip it around. And that is a 20 move solve. And that is the maximum. That's one of those cases where it's the maximum number of turns for the optimal solution.
Explain maximum in that capacity. It seems like you're talking about the fewest number of moves to solve.
That's what makes it difficult to explain. It is the fewest number of solves, but 20 is the largest number of the fewest moves to solve the cube. So essentially, if you that super flip position, let's say that was the hardest permutation. That's the one that takes the most moves to get back to the starting position. So the optimal solution in the super flip position is the largest. So and the optimal solution is 20. So every other optimal solution, so minimum number of turns, is smaller than 20. So it's hard to explain because you have to.
I understand that.
Yeah.
You
Okay.
explained it really well. Thank you.
All right.
Is it safe to say that if I knew what I was doing, I should never have to do more than 20 moves?
No. So in competitions, there is a section where people have an hour, I think, to come up with their best optimal solution. And the lowest a human has ever gotten it down to is 23. And that might have been a really easy solve. So yeah, you're not going to be able to.
Yeah, but I'm asking that as a mathematician. I'm pretending that I'm omnipotent, that I can do anything.
Okay.
And you all know I'm pretending. So if I were not a mere mortal, if I were God, then you give me a cube, it should never take me more than 20 moves.
Exactly, yeah.
You've also, you talked about the 50 different algorithms that you can use using the, is it
Friedrich method, yeah.
Friedrich method. If you, like, it looks like what you do is you kind of play around with it until you get something that you recognize and you know what to do with it from there. If you knew, maybe I'm mischaracterizing what you're doing, but if you knew if you were able to memorize all of those, would any cube that you were handed, would you have an algorithm that you were going to then going to follow without having to move it around until you found one that you recognized?
Well, that's not exactly what I do. So when you start off with every layer is messed up, right? So there are so many different permutations that there could be. Like it's at 43 quintillion at that point. But as you solve the layers going up, you're reducing the number of permutations that there can be. So then when you get the first two layers done, then you're looking for what permutation you have. And then there are algorithms to solve those ones. So there's 57 to orient the last layer, and then 21 to permute it. So because there are 58 different ways that it can be oriented, and then 22 different ways that it can be permuted, my intuition is that the number of permutations when you get to the last layer is 58 times 22. I think that you might have to subtract out repetitions in that, but yeah, that's.
You didn't memorize all of those, so when you get to that last layer, is there one that says, well, this isn't one of the 20 things that I've memorized. If I just do this move, it'll scramble it, and then that's kind of what I think he was asking.
Yeah, so because I don't know all of the 57 orientation algorithms, what I do is I look for how many edges are oriented. If there are no edges oriented, then I get 2 of them oriented, and then I get the rest of them oriented.
Sometimes that's an algorithm.
Yeah. So yeah, I use algorithms for that. I use 4 different algorithms for that. If there are 2 already oriented, then I just get the other 2 oriented using one of those algorithms.
There may have been a more efficient algorithm to go straight to it.
There definitely is.
You just have one that says, okay, I can do these 2, and then once I get there, I know what to do from there.
Yeah. And then once the edges are done, I move on to the corners, and that's how that works for orientation. For permutation, I do the corners first, and then the edges. So yeah, it takes more than one step. Yeah.
How does the solving it change when you have an even number of sides for 2x2 or 4x4 that doesn't have a center?
Okay, so yeah, that's a good question. So for a 4x4, so the method for anything larger than a 3x3 is basically, for most methods, you reduce it down to a 3x3. So in this case, I have 2 edges here instead of just 1. So I pair them together, so then it just looks like a larger 3x3. I pair all these centers together so that it's just a larger 3x3. But there is a case that is very tedious to solve because sometimes these edges can be flipped around. It would be like doing one of those illegal moves on a 3x3. You'd be flipping one of the edges around. And you have to do this long algorithm to solve that. And that happens because, I don't know the details of it, but basically there's an even number of edges here, so they can be flipped with each other and then flipped and then misoriented. So you have to, I don't know exactly how it works, but that's the reason that is, because when you do flips here, you have to do an even number of flips. And with this, when one of these, or when both of these edges are flipped around, that is an even number of flips because you're flipping one and then you're flipping the other. So that's how that works. And that's why there's the parity, as we call it, when one of those edges are, or when both of those edges are flipped. So, yeah.
So you can solve all of them on the table, correct? Which one is the hardest?
There is one that I cannot solve. It's this one, because it's just a regular 3x3, but it's the Sudoku puzzle, so I can't solve that one because I don't know how to line up all the numbers correctly. So there is one that I can't solve.
The rest of them, though, you can solve.
Yeah.
The rest of them, which one's the hardest one to solve?
That is a good question. I would immediately say this one because it's not mine, it's my cousin's, and I've only solved it once or twice. So the problem is I don't know the color scheme, so I don't know which colors go next to each other, so it makes it more difficult for me to solve it. So that I would say that one is the hardest for me. Yeah?
What's your average and your best time with 4x4?
I don't know my best time. I think it's like 1 minute 30 or something, but my average is about 2 minutes. So.
Like that.
5x5, my best is somewhere around probably 2:30, and my average is about 3. Yeah?
For your 3x3s, which one do you prefer the most, like mechanically speaking? Which?
I just got this, it's called the Gans 356 Air. It's one of the cubes that is used by the world record solver, so it's well above the other ones I have. So this one is definitely my favorite. So.
Do you have to special order those now? Because it seems like most of the stores just have those solid plastic, no sticker cubes.
Yeah, so this is my first Rubiks Brand. I got it out of the store for $10, and it is garbage. It's awful. The Rubiks Brand, besides like the dollar store cubes that you can get, the Rubiks Brand, the original Rubiks Brand, is actually the worst one out there. And unfortunately, it's the one that's most commonly in stores. So I special ordered this one online, and you pretty much have to do that to get a decent cube.
When you search for them, you can't use Rubik, because Rubik's, what do you search for? Are they titled, you know?
I actually have a specific website that I go to that has just a ton of different, that's where I got pretty much all of these ones from. So.
Do you have the keychain?
I do, right here.
That's awesome.
Yeah.
I'm envious of that.
Yeah.
So which one's your favorite to solve?
I'm going to have to go with a classic 3x3. Yeah.
Have you tried to solve it in front of a mirror?
I have. It's really difficult because, well, it's harder to not look down than it is to actually solve it in a mirror. But if I, essentially, it's really hard until I get to the parts that are algorithm-based. So at that point, I just, pick a point and just focus on it and then just do it by memory and not even look at what I'm doing. Yeah?
How is this going to help you in life?
Okay, so,
You got to do a presentation.
yeah. This helps with, so I'm hoping to go to dental school after undergraduate, and a big part of the DAT, which is the dental school test, it's like 3D, like imagining things in 3 dimensions. So like they'll give you this abstract shape and they'll say, how can this fit into this keyhole? Or which keyhole is the correct shape for this to fit in. So you have to imagine it in your head and figure out which way it goes in. and this helps with that a lot because I have to imagine which way the pieces are going to move around and which shapes they're going to become. And also in organic chemistry, I've had to help out my brother with visualizing some of his problems. So,
Do you view this as like an art form?
I'm sorry?
Do you view this talent and practice talent as like an art form? Do you consider yourself more of an artist when you're doing this, or?
No, I don't consider it an art.
Now, wait a minute, hold on. You said something, we
I
talked a
did.
week ago. I'd like you to say it now if you remember what it was.
Yeah. Okay. So.
It was wonderful. It made my day.
So I play piano as well, and the way that I memorize algorithms is the same way that I memorize songs on the piano. So essentially, I'm imagining myself playing a song on the Rubik's Cube with my fingers. So, I guess.
I think, and I know I couldn't solve a cube to save my life, but I think just based on watching you and what you do, I think it's much more art than you would clearly. I think you're very much an artist.
All right, I suppose you could consider it an art, yeah. It all depends on your definition of art, then, I suppose.
When you're thinking about it like a song, are you, are the moves coded in any way? Do you hear a sound, or do you
I actually,
tactile sensation?
so I use muscle memory, like the same thing that I do on a piano, to memorize algorithms, but I also listen to the noises that it makes, and it develops kind of like a rhythm. So like for, I think it's called the Z Perm. There's the distinct sound that I'm memorizing, and that's why it makes one-handed solving so difficult for me, because I can't go that fast when I'm solving one-handed. So the rhythm is different, and it just makes it so much more difficult for me because I'm listening for that rhythm, and I forget what I'm supposed to be doing because I can't hear the sounds I'm used to.
I think
Yeah.
you should patent a new one where there's a musical note for each one.
I've definitely thought about that.
Well, when you watch people who memorize pi or some long series of
I memorize pi as well, so.
yeah, but you'll watch them tapping different parts of their body or tapping out, and they actually have an integration of that rhythm with their numerical memory that helps with recall, and it sounds like that's a similar mnemonic that you use.
Yeah, I don't like specifically, I didn't start memorizing them that way. I didn't think, okay, I'm going to listen for the sounds that it makes or anything like that. But yeah, eventually I did notice that the sounds help a lot in the way that in the rhythm that they have. So, all right.
Thank you.
Yeah, thanks for having me.
Really interesting. I have more questions, but I'm going to stop asking now
All right.
because it's almost 4 o'clock. But I would imagine that our speaker would be happy to hang around for
Yeah.
a few minutes.
Yeah, if you want to come up and scramble some of these.
Talk about cubes and answer questions. Now, our next seminar, I believe it's now officially Wednesday, March 21st. Our next speaker happens to be sitting right here. Katrina, would you want to say anything, or?
Sure.
Okay.
Basically, we're going to be talking about is math a language, and if that is the case, how can that better help with both teaching and understanding, especially those who do not intuitively understand mathematics and how it works, and how that could help us see math on a deeper level than pushing symbols around.
Trina and I talked about this a little bit yesterday. She was kind enough to stop by, and something that we discussed yesterday just came to me in class today in Calc 2, because I wrote a very simple equation on the board, which was dense with information. So I actually stopped for a moment and said, this is where the next talk is going to be happening. So more information will be coming out. That is about a week and a half after the end of our spring break, so it's good. Fisher, thank you so much.
Yeah.
It was fantastic.
Thank you all for coming. Yeah.
Please, before you leave, we have food, we have drink. Take as much as you'd like, 'cause otherwise I got to carry them all down the street.